Okay, welcome back. So what we're doing now is trying to connect the study of these series that we've been working with to approximating functions. And the first step is to consider the approximation of functions by polynomials. Okay. So 9.7 Taylor polynomials and approximations. Okay. So as I noted in class, the what is this all about? It's you can have, so take for instance the exponential function. Okay, this is f of x equals e to the x. We can do an approximation of this function with a linear function, the equation of a line. So put a line right there, and we can find the equation for that line, noting this point right here is 0 comma f of 0, which of course is 0 comma 1. And using the slope at this point, so note the slope of this tangent line should be f prime of 0. The derivative of e to the x is just e to the x, and so we have e to the 0th power, which is 1. And then we have a point on there, 0, 1, so we can use point slope form to create an equation here. Okay, so we'll have y minus 1 equals the slope, which is 1 times x minus 0. So y will equal 1 plus x. Okay. So polynomial approximation of this curve, and certainly for very small regions, like if I took a box right here and kind of looked at it, the function and the polynomial are pretty close to each other, right? So we would have my exponential going like that, and then the tangent line is very close to the actual function there. Okay, so I recognized this earlier, and then I said we could amp this up a little bit more. We could say p sub 3 would be 1 plus x squared over 2 plus x cubed all over 6. And the way we did that was kind of putting in more and more derivatives, sort of more conforming, like extra slopes. Okay. And that's the way you would build these functions. But if we consider them trying to approximate e to the 1, maybe, with this polynomial p sub 3 of 1, the end result is basically just a summation, a series, right? I mean, in this case, it's a small series. 1 plus, I plug 1 in for x, I get 1 plus 1 squared is 1 all over 2 plus 1 cubed is 1 all over 6. Okay, it's a partial sum, right? So there's a connection between the series we've been studying, the partial sums, and these approximations. Okay. Probably the big question then is, how the heck did I get these other terms? I think the first two terms are clear. I kind of showed you how I did that. I built that just with what I knew from pre-algebra and equations of lines. And there's a little bit of calculus here, right? Because I have to be able to take the derivative of the function. The question becomes, how do I get these things? And then later on, we consider, rather than just partial sums, in these cases polynomials, we consider infinitely long polynomials. In other words, those will be called the power series. Okay? And it turns out the power series, so long as this thing has infinite number of derivatives, will be kind of, we could use the power series to learn a lot about the actual function. They'll be equal, I believe, in the end. So that's we're connecting now to what the main goal of this chapter is. It's been kind of I've kind of alluded to it. Unfortunately, the book doesn't allude to it as much as I do. But this is the idea. Okay, there's a connection between sums and these polynomial approximations. Okay, so how do I get these extra terms right here? You know, how did I construct those? How did I know? You know, it was a fraction 1/2 and 1/6. Okay, so that's where we sort of get back to where the book is working. And first we consider polynomial approximations around some value x equals c. So in this problem, we decided to center our polynomial around c equals 0. Okay, so I built this thing off of this point right here. And in general, you know, we'll do that. So, you know, what do we want with our polynomial? We desire that the function evaluated at c and the polynomial evaluated at c are going to be the same. In other words, this point is the same on the line and on the function. Okay? So we desire this to be the same. And also, it would be nice if all the derivatives would be the same too. And it becomes kind of a system of equations that we can solve for these coefficients. And that's kind of where it's going to happen. So, and also we desire f prime of c to equal p prime of c, etc. So f double prime of c we wish to equal p double prime of c, and it forces kind of the shape of this to conform to the shape of that, on and on until f nth derivative of c equals the nth derivative of this polynomial at c. Okay. Okay. So we begin with you can begin with a first degree polynomial and kind of see how that works. I mean, we had a process for developing this first degree, but let's see it in this new context. Okay? And we'll work with e to the x centered at 0 as well. So example 1, we want to approximate f of x equals e to the x with a first degree polynomial, in other words, the equation of a line, at the center c equals 0. Okay, so first, what does a first degree polynomial look like? We'll notate it p sub 1 of x, and we'll give the constant terms names. Instead of, you know, mx plus b, we're going to write it a sub 0 plus a sub 1x. Okay. From above, these requirements are going to allow us to solve for these coefficients a sub 0 and a sub 1. So note, we wish, you know, so we have to figure out the derivatives of this f of x and the derivatives of p1 of x. And then we have to evaluate them at 0 and set them equal to each other. The polynomial will get annihilated by the derivatives after the second derivative. So p1 prime of x is just going to be a sub 1, and then yeah, that's right. It'll just be a sub 1. So it gets annihilated at the second derivative. So when I play around with this, I only need to find the first derivative over here. So f prime of x equals e to the x. And then I have to evaluate these at the center. So f of 0 is e to the 0, which is 1. F prime of 0 is e to the 0, which is 1. Over here, p1 of 0 is going to be a sub 0. And then p1 prime of 0 is going to be a sub 1. Just plugging 0 into the corresponding equation. Okay, so we want to equate these guys, and from that we get, you know, what do we want? We want f of 0 to equal p1 of 0, which means we want a sub 0 to equal 1. And then we also want f prime of 0 to equal p prime of 0, which tells me I want 1 to equal a sub 1. That in turn, we've just figured it out. We've solved for the coefficients on our polynomial approximation, and so p1 of x equals 1 plus 1 times x, which is exactly what we found it to be using pre-algebra. Right. So great, good stuff. We want to mechanize this patterning, or find a pattern for this process. And in order to do so, we kind of want to look at a higher degree example. So for instance, let's try a third degree. Okay. Find a third degree polynomial approximation at c equals 0. So the form of this guy, which we'll call p sub 3 of x for third degree, is going to be a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3 x cubed. Okay. And from this example, I'm hoping to kind of find a general methodology that will give me any approximation, so long as I know kind of the function and its derivatives and what it evaluates to. Okay. All right, so in this case then, our sort of table of derivatives will, we have to go to the third derivative in order for this to work. So I'll just kind of go over here. So f of x, f prime of x, f double prime of x, and then f triple prime of x. Okay. We've picked a very easy function to work with, so this is always e to the x. And then I need to evaluate that thing, these guys, at 0. Okay, and they're always going to be 1. Then the polynomial, and then get its derivatives, and then we need to evaluate those derivatives as well. Okay. So the thing about taking derivatives of these polynomials is they kind of will produce factorial expressions. Okay, so in our when we finally get our formula for what's going to be the Taylor and the Maclaurin polynomials, you're going to see factorials in the formula, and it's because of this process here where we're taking repeated derivatives of polynomials, and those exponents are coming down in front. So at the first derivative, the a sub 0 constant will go. I'll have a sub 1 plus 2 a sub 2x plus 3 a sub 3x squared. At the next derivative, the a sub 1's gone, and I have 2 a sub 2 plus 3, and I bring down the 2, so times 2. You could write 6, but it's more instructive to look at this derivative as 3 factorial. Okay, and then 2, this of course is 2 factorial. Okay, so this would be, then at this point, you get rid of this guy, and you're left with 3 factorial times a sub 3. Evaluating each one of these, p sub 3 of 0, p sub 3 prime of 0, p sub 3 double prime of 0, p sub 3 triple prime of 0. The first guy gives us a sub 0, the second guy a sub 1, this third guy 2 a sub 2. This guy gives us 3 factorial a sub 3. Okay. And then we want to use these and these to get our coefficients for this guy right here. I need to figure out the coefficients, a sub 0, a sub 1, a sub 2, a sub 3. So I need to equate these guys, and then I'll have my answer. So a sub 0 has to equal 1. A sub 1 has to equal 1. 2a sub 2's equals 1, but I have to solve for a sub 2. So let's note 2a sub 2 equals 1. That tells me that a sub 2 is 1 all over 2. Okay. And then the final one we have 3 factorial a sub 3 equals 1. So 3 factorial a sub 3 equals 1. In other words, a sub 3 will be 1 all over 3 factorial. And in general, we're kind of getting at the pattern. It may not be clear yet, but what's going to happen, you'll have the coefficients on your polynomial will always be 1, which is f of 0, and then the next coefficient will be f prime of 0, and then this will be f double prime of 0 divided by 2. This will be f triple prime of 0 divided by 3 factorial, and so on. Okay, so, but anyways, right now we have a p sub 3 of x is 1 plus 1x plus 1/2 x squared plus 1 over 6 x cubed is our approximation. But, you know, in general, a sub 0 is going to be equal to f of 0. A sub 1 will be equal to f prime of 0. A sub 2 will equal f double prime of 0 divided by 2. Oops, sorry, it's off the page. A sub 3 will be f triple prime of 0 divided by 3 factorial. And then a sub 4 will be f4 of 0 divided by 4 factorial, and so on and so forth, comma, all the way up to a sub n will be the nth derivative of f evaluated at 0 divided by n factorial. Okay, so then these things will be the coefficients on your polynomial back here, the a sub 0, a sub 1. It's telling you the coefficients. So as long as you can evaluate the function at the center and the function has n derivatives, you can find an nth degree polynomial approximation for the function. Okay, so what we have kind of produced then are the Taylor and Maclaurin polynomial approximations, formulas for these. Okay, and so what do those look like? The Maclaurin is centered at 0, so p sub n of x using these coefficients. It's just a polynomial with coefficients based off of the function and its derivatives centered at c. So for Maclaurin, c is equal to 0. Okay, so we'll have f of 0 plus f prime of 0 times x plus f double prime of 0 all over 2 times x squared plus f triple prime of 0 all over 3 factorial times x cubed plus plus f, the nth derivative of f evaluated at 0 all over n factorial times x to the n. Okay, and then for the Taylor, that's when c is not equal to 0, and it's basically just a shifted version of this original polynomial. So the Taylor will look like this: f of c plus f prime of c times, and this is where it's a little different. You have to shift over by c, plus f double prime of c all over 2 times x minus c squared, plus f triple prime of c all over 3 factorial times x minus c to the n, right? And then plus plus the nth derivative evaluated at c all over n factorial times x minus c to the n. Whoops, this should be to the third, obviously. Okay. Alrighty then, so you know, in the book, you're going to be finding these Maclaurin approximations or the Taylor approximations. comes down to kind of finding the derivatives, evaluating the derivatives, and then copying and pasting them into our formulas. So let's find the nth Maclaurin polynomial for sine of x. So we have f of x equals sine of x, and we want n to equal 5. So we want a fifth degree polynomial for sine x. So in order to do that, I need to find the first 5 derivatives of sine x and then evaluate them. Okay. So sine of x is cosine, and then negative sine, and then negative cosine, and then sine, and then cosine again. Evaluating them. So we want a Maclaurin, so they want you to center it at c equals 0. Okay. So I'm evaluating all these at 0. And these become basically the coefficients on my polynomial, except you always have to divide by the corresponding factorial. Okay. So 0, 1, 0, negative 1, 0, 1, and then P5 of x in its most basic form. I mean, literally you can set it up like this as a fill-in-the-blank type thing. Right, and then it's just copy and paste, put all of these in here. So 0, 1, 0, negative 1, 0, 1. And, you know, you clean it up a little. So x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Okay. Let's do a Taylor polynomial. So this is number 25. Find Taylor polynomial. So this time, when you're talking Taylor, c is not 0. Okay. We'll look at 25. So we have f of x equals 2 over x, n equals 3, and c is 1. You know, literally, you would never really want to find a polynomial approximation for this thing. It would be silly. The deal is that this thing is kind of related to the natural log, because the natural log 2 ln x, its derivative is this. Okay, so I think what they're alluding to is that we're going to be using these polynomials to approximate natural logs. Anyways, I don't know what the book was thinking, but let's take a look here. So I need the first 3 derivatives of this thing. I'll rewrite 2 over x is 2x to the negative 1. So f prime of x is negative 2x to the negative 2. F double prime of x is, sometimes it maybe is a little better to keep things separate. So negative 2 times negative 2, I'm just going to write 2 times 2x to the negative 3. F triple prime of x is going to be 3 factorial times 2x to the negative 4. So then evaluate all these at 1. And these sort of become our coefficients. So this would be 2, negative 2, 2 times 2, 3 factorial times 2. Then go to your Taylor polynomial. I'm going to call it P sub 3 of x. Okay. And this time we're plugging in our boxes. Will look like this. Just jump in your coefficients. And if you keep them separate, you see that these coefficients are going to cancel out the factorials. So we're left with 3 factorial times 2 here. This 3 factorial will cancel out. And it's kind of the purest Maclaurin polynomial there. You know, when you're maybe that's the point. When you're working with these guys, you kind of get out pure polynomials without these constant factorial factors involved. 2 minus 2 times x minus 1 plus the 2 factorials cancel, so you have 2 times x minus 1 squared, and then plus the 3 factorials cancel. I probably lost a negative in there somewhere. Yeah, it should be negative. So this is negative. So it would be minus 2 times x minus 3 cubed. All right, so great, right? So what? Yeah. How good are these things? You know, supposing I get one of these polynomial approximations, what good is it? How good is it? Do I know how good it is? All right, so how many terms do I need? And we saw this kind of issue before with the alternating series estimation theorem. And you'll get the same kind of problems here. So the problems are asking, how many terms do I need for the approximation to be less than this error? Or if I have 6 terms, how close is that to the actual value? Those 2 questions get kicked back and forth in the book, right? So section 3 then, approximating using Tailors polynomial. And from the book, we get Tailors theorem, which will say the error between the function, the actual function, and its nth degree Taylor polynomial will be equal to this r sub n of x function. Okay? And that r sub n of x function is basically, it's a lot like when you dealt with the alternating series estimation theorem. This thing is basically the next term that would have been in line in the polynomial, sort of, right? So it's the n plus first derivative evaluated at some special number z all over n plus 1 factorial times x minus c to the n plus 1. Okay? Right, so this z value, the way I remember it being read to me or explained to me, has something to do with like a mean value theorem. There will exist this point in the interval from between the point you're trying to approximate and the c point, such that this thing exists. Okay, if we have some criteria fulfilled, and basically you need n plus 1 derivatives, and that's about it. Okay, so anyways, it looks intimidating in the beginning, but if you just think about it as this thing being basically the next term in line after your nth degree polynomial term, then it's kind of easy to remember. It's like if you know this, then you kind of know this remainder part. It's just going to be the next term in line. So anyways, these problems can be a little bit difficult in playing around with. In general, when we're trying to find a bound for the error, or in general, we can find a bound for this area, so we can work with this formula without having to actually find this z value. In general, we will bound the error this r sub n of x function by noting that the absolute value of r sub n of x will be less than or equal to the maximum of this function on this interval from x to c. Okay, so sometimes c can be less than x, so I want to be a little bit careful about. So I'll just say interval I from x to c, and we're maximizing this function f to the n plus first derivative of f. Okay. And everything else is the same, n plus 1 factorial, and then over here, absolute value x minus c to the n plus 1. Okay. So let's try it and see how it goes. Okay. So example 8, use Taylor's theorem to approximate sine of 0.1. By p sub 3 of 0.1 and determine its accuracy. Okay, so first off, what is then this polynomial approximation? P sub 3, did we do sine x already? It's x minus x cubed all over 3 factorial will be p sub 3 of x. And then we want to approximate sine of 0.1 with this thing. So we're plugging 0.1 into this. Okay. And you can put that into your calculator. You can do this by hand, really. But I'm getting 0.0998333. Okay. So we're approximating sine of 0.1 with this number. We want to know how good of an approximation that is. So we go back to this Taylor's remainder theorem and play around with that. Okay. Okay, so to play around with this thing, then there's a whole bunch of variables we need to find, right? We need to know n, we need to know x, we need to know c. We needed to know what this entire expression is as well. In this case, we know some of that information, right? So we're looking at finding r sub n of x. Which will be less than or equal to the max, the absolute value of the n plus first derivative on this interval all over n plus 1 factorial times x minus c to the n plus 1. What do we need to know? We need to know n. And this is usually how I start these kind of problems. I just kind of list the unknown variables. We need to know x, we need to know c, and we need to know this item right here. We need to know what is the max of the absolute value of the n plus first derivative on this interval from x to c. Okay? So what are the n, x, and c? Do we know any of that? Well, we know n is 3. That's the degree of the polynomial. So p is 3. I know x is this 0.1 number that I'm putting in. This polynomial approximation, it's said in the book, it's a Maclaurin. Okay, so the c value is 0. And then the real troublemaker is this guy right here. I need to maximize the n plus first derivative of my function. Okay, so I note, or I need to maximize the n plus first derivative, and in particular the absolute value of that. And you could use calculus to do this. Basically find what this is and then take its derivative and maximize it on that interval. So in Calc 1, one of the first things you learned in the applications of derivatives was to maximize a function on a closed interval. And that's exactly what you're doing here. You're trying to maximize this thing on the interval from 0 to 0.1. Okay. Okay. In this case, it turns out to be quite easy because the n plus first derivative of sine is either going to be sine of x or a cosine of x or negative sine of x or negative cosine of x, right? But if you take the absolute value, then we could be assured it's one of two things, sine of x or cosine of x. Okay, and to maximize that, that's simple because these guys are both less than or equal to 1. Okay. Right, so essentially what we have then is a bound for this guy right here. Okay. This max value will be 1. Okay, and then I can go back now to my remainder formula and fill in the blanks. So R sub 3 of 0.1 will be less than or equal to 1 all over 3 plus 1 factorial times the absolute value of 0.1 minus 0 to the 3 plus 1 power. Okay? And then if you evaluate all that business, you get 0.1 to the 4th all over 4 factorial, which is equal to 0.0000004. It's an awesome approximation. And all you have are 2 terms. I mean, it just suggests that you can pretty much throw the trig function in the trash and just work with a 3rd degree polynomial, and you'd be happy, you know, for all our intents and purposes. It sort of works that way. So, you know, great. Okay. Let's move on then and look at the other side of the coin in example 9. So we're trying to figure out how many terms do I really need for an approximation to be less than some error. Okay, so for the difference between the actual function and this polynomial to be less than something. So I require, I need an approximation of the natural log of 1.2 to be less than 0.001, and I'm centering my approximating polynomial at c equals 1. Okay, okay. So I need to know how many terms, you know, what degree polynomial. Okay, what degree polynomial is required. Okay, so again, I'm thinking about this R sub n of x object, R sub n of x. I need this max thingamajig on the interval. I need this n plus 1 factorial and this x minus c to the n plus 1. So there's always going to be these 4 unknown things that you need to figure out before you can start turning the crank. So the max of the absolute value, again, we're going to need that thing. Okay, that's kind of an unknown. The c value, in this case, we know that's 1. And the x value is the thing you're trying to put into your formula. So that's 1.2. And then the n value is also unknown. So n I don't know. Okay. Okay. The answer to this question will be the n value. Okay. So in order to unlock everything, I'm going to have to figure out this guy right here. Okay. So I require, or I want to find the maximum of the absolute value of the n plus first derivative of x on the interval from 1 to 1.2. So basically you're trying to maximize this function on a closed interval. And for that you use calculus. So I need to figure out what this function is, what this I need to find this g of x function, which is equal to the absolute value of the n plus first derivative of f. Okay. Okay, so what I'm going to do is kind of just look for patterns. Okay, discrete math. What do they call it? Freaking forget what they call it. An iterative method, maybe something like that, to finding patterns. So you start with f of x, right? So f of x is the natural log of x, and then you keep going. F prime of x is going to be 1 over x, which of course is x to the negative 1. F double prime of x is going to be negative x to the negative 2. F triple prime of x is going to be, bring down the negative 2 now, so you get 2 x to the negative 3, and then f, the fourth derivative is, and I'm going to write negative 3 factorial x to the negative 4. Okay? So I think the pattern will be more obvious then. The fifth derivative is going to be 4 factorial x to the negative 5. And then I think I see the pattern. The nth derivative of x will equal, well, when it's odd, we have positive, so we need this negative 1 to the n plus 1 factor. And then it's 1 less factorial than the degree of the derivative. So when you have the fifth degree, you have a fourth factorial. So when you have an nth degree derivative, you have n plus 1, or sorry, n minus 1 factorial. And then we have x to the negative degree of the derivative, right? So if it's a fifth derivative, you got a negative 5. So negative n. Okay. We need the n plus first formula, so that let's take the derivative of that thing. And what do you get? Well, you bring down another negative 1. So in particular, negative n is going in front. So I'll have negative 1 to the n plus 1 plus 1, so n plus 2, which is just going to be the same as n. And then n times n minus 1 factorial will be n factorial, and then x to the negative n plus 1. Okay. Then what we're working with, what we want to find is that g of x, which would be the absolute value of that. So g of x, which equals the absolute value of the n plus first derivative. So regardless of what the heck, even if I made a mistake on this negative 1 term here, which I don't think I did, it's going to get obliterated by the absolute values. So g of x is going to just be n factorial times x to the negative n plus 1. Okay? And then in turn, I need the derivative of that so I can maximize this on the closed interval. So I need to maximize this on the closed interval from 1 to 1.2. Okay. And so I take its derivative, g prime of x, then will equal, bring down a negative. So you have negative n plus 1 times n factorial, which will be n plus 1 factorial. And then x to the negative n plus 1 minus 1, which would be negative n minus 1 minus 1, which would be negative n minus 2, which would be negative x to the negative n plus 2. Okay, if we drop that to the denominator, we have negative n plus 1 factorial all over x to the n plus 2. Okay. This thing is, the derivative of g of x then is less than 0. So there's no critical points in this interval. Usually what you do is find the critical points and then evaluate the function at the endpoints, and you figure out what the max and min is that way, and at the critical point. So to find the maximum on a closed interval, find the derivative, set it equal to 0, find the critical numbers, substitute the critical numbers into the original function along with the endpoints. That will tell you what the maxes and mins are. In this case, there are no critical numbers. So all we have to do is evaluate the function at the endpoints. But because we have a derivative that's decreasing, we know that on this interval from 1 to 1.2, the function must be going down like this. Right? In other words, this function is maximized at the left-hand endpoint. Okay? So finally, then, the maximum should be g of 1. And so g of 1 equals what? Well, it equals n factorial times 1 to some power, negative n plus 1. 1 to any power is just 1, so g of 1 equals n factorial. Yay! Okay, so I got basically all I need for this to pan out now. So I've cleared this part of it up. This is actually equal to n factorial. Okay. Okay, so I go back to that function. I go work with my remainder function. I have the absolute value of r sub n, I don't know n, of 1.2. That's going to be less than or equal to n factorial all over n plus 1 factorial times 1.2 minus 1 to the n plus 1. Oops, I hope I didn't lose you there. So r sub n of the point we're evaluating, so we want ln of 1.2, so you put 1.2 in there. This was the maximum of that g of x formula, it's n factorial, all over g of n plus 1 factorial, and then this is x minus c. Okay, so x is 1.2, the center is 1, and then we have n plus 1. Okay. We want this thing to be less than 0.001. Okay, so let's first clean it up. N factorial all over n plus 1 factorial is the same as 1 all over n plus 1. 1.2 minus 1 is 0.2. Okay. And then finally, we desire this expression, 0.2 to the n plus 1 all over n plus 1, to be less than 0.001. Okay, and then you just do trial and error to figure out your n value, right? So try n equals 1 by trial and error. We note the following: when n is 1, we get 0.2 squared all over 2, which equals 0.02. That's not good enough. When n equals 2, we get 0.2 cubed all over 3, which equals 0.003. It's not good enough. So we must probably want n is 3, so 0.2 to the 4th all over 4 equals 0.0004, and that's definitely then less than 0.001. So at the end, we require a third degree, we want n equals 3, third degree polynomial approximation. Okay, that's the deal. See you next time.